Alright, so right here we got a miniature version of the friction coefficient. Right here, this ramp is the snow-covered wood that we use in the experiment. This box of matches is our
snowboard, toy snowboard.
Snowboard, yep. So right here, how we conduct the experiment is we took this first angle of elevation, which is represented right here. Right there,
Oh,
yep.
Yeah.
And then we measured the distance between that the toy snowboard has to travel. And then so that gives us our known change in x. So that's known. Okay. And then we took the time it took to travel that known distance just by using stopwatch. Every time it hit here, we'd have a set system to measure that. So our time is known. Cool. Known. And then our V0, of course, is just going to be 0 because it starts at a standstill. So our V0 is known. So really, what we're setting up here is we're going to compare the theoretical acceleration compared to the actual acceleration. That'll give us our friction coefficient. So using this equation right here, we can just simplify this down into change in x equals 1/2 AT squared. And that will give us just our basic, our real acceleration. And then using basic geometry, we can make a right triangle out of this angle. That's a Mr. Meerwald right triangle. And basically calculate that acceleration right there. Nice. So then, using Newton's second law, we can just say the sum of the forces is going to be equal to the resultant force. But you can re-express this as saying the theoretical force minus your retarding force equals your actual force. So using the kinematics equation, we can solve for this. Using our trigonometry, we can solve for this. And then we can simply re-express this using trigonometry as a function of mu. And using that process, we can simply calculate it without massing, which results in a lot less scientific error. And sets up a good system. And that's how we found the 0.03 friction coefficient of wood, or plastic injected.
No.
Injection molded plastic
toy snowboard
on snow covered wood.